At this time, I want to continue with the discussion of neural nets by training a neural network which does one of the very common things that people really have considered or thought of successful for neural nets, which is labeling of images, classification of images. In 2012, with ImageNet, really the ability to train a deep neural network architecture at scale. This was really allowed by having the data set, the ImageNet data set, plus also advanced computational power, allowed us to really start seeing and exploiting the structures of deep neural nets. So ImageNet was a really critical transition in what has revolutionized the field of modern deep learning architectures. So details of this, code base, everything can be found here at databookuw.com. It's based out of a chapter in chapter 6 out of this book on data-driven science and engineering. So let's get right to it. I want to show you an architecture. And this is something you might find all over the internet, is pictures like this. And what it is sort of this canonical architecture that people have started developing for image labeling and classification. And so let's go through some of the features of this. Typically, there are many layers. So this is just it's a representative. If you look on the internet, just type deep convolutional neural nets, you'll see a lot of different architecture structures and styles, but a lot of it has this kind of base schematic to it. So I just want to highlight the kind of structures that people have been exploiting that have been successful in image processing. And then we'll go through some code and show you how you might be able to actually implement something like this in practice. So typically, there's an input, and the input is an image. And what the goal of a lot of the image processing is to take that input and provide it with a label. So oftentimes what you have in ImageNet, for instance, is you had a set of images with classification labels on the back end. So you're going to go from this input layer all the way over here to the output, where the output is a label. So for instance, earlier in the lectures on neural nets, we started off with very simple labels and very simple images. Dogs and cats. Right? So there's only 2 labels at the back end of this thing. But you can imagine in vision processing, you might have a very large, diverse set of labels. Pizza, car, house, anything you can imagine would be part of this, and labels can become even more sophisticated. You know, people having a picnic. So these labels are typically provided by someone who's gone through and hand labeled these images and provided the output that you need and the training data to take this process and learning all the weights associated with this complex neural network architecture. Okay? So by the way, this is also very important in the structure of, for instance, cameras that are on self-driving cars, right? So what a camera needs to do on a self-driving car is, as a car is driving around, is to label the entire scene. There's a pedestrian, a cyclist, other cars, here's the road. So all of this is done in sort of some kind of architecture of this nature. So let's walk through. 2 kind of functions I especially want to highlight for vision is this idea of convolution and pooling. So these are going to be oftentimes the 2 key components of making computer-based algorithms for vision. Okay? So you start off with your image, which is typically some high-dimensional picture. So think about even 4K video frames or HD camera. Everybody has smart technologies with them, whether it's cameras or video, that produces very high-dimensional inputs, which are pixel space. And typically, pixel space also has RGB colors, and that's 3-dimensional. And so that's all in here. This is a high-dimensional input space trying to get mapped out to the label space. And again, the label space can be a variety of things, but the example we've worked with so far, cats, dogs. Okay? But you can have a much, much broader set of labels on the back end. You may have thousands of labels, tens of thousands of labels, and your goal is to take an image, run it through this network, and produce an accurate label for that image. So how this works. Well, here's my input, and we're going to first talk about convolution. One of the interesting things about what a convolution does is it looks at parts of the picture. So here is a little convolutional window that you can slide across the entire image. Okay? So the idea is within that window, you look for features. This is important because if there was a dog in this picture and maybe was in this right corner, to just look at the entire picture would maybe not be the most useful thing, but to have a sliding window that goes across the entire image and in each little subblock tries to see what are the features in the subblock associated with the labels, that's the kind of thing that it should start learning. And in fact, you can create lots of layers of this convolutional window. So every time you randomly start this, if you restarted this network, you might produce a filter from the input space to a convolutional space. So every single one of those windows, here it is, here's for instance, here are the pixels in that convolution window, produces through a nonlinear output function, which could be ReLU, linear, sigmoidal, whatever you happen to bring onto this, produces an output which gives you some evaluation of what's going on in that convolutional window out to some functional output. And you're going to train the weights to give you some kind of representative figure here that gets you from the input to the output. Every time you train this, you can produce a different transfer function f. In other words, this transfer function f has all the neural network weights that are here in this network conveyed into that function. So if I retrain it with a different random start, I will generically get a different weighting function. And so you can do this multiple times to produce lots of different filters to a convolutional layer over here. Not only that, you could apply different type of activation functions. You could put a ReLU, a linear, sigmoidal. So what you're producing here, what I'm trying to show here is through this process of convolution, through random starts, through different activation functions, you can produce a set of features in this convolutional space representing this input images. From the convolution window, typically what's done in a lot of these image processing type ideas is you follow it up with a pooling window. What pooling does is it takes a square, such as this, and it produces an average of that square. Oftentimes it's called max pooling, which is it takes these pixels that are in here and it just simply produces what's the max value down at this level here. And notice what happens in this process. It's a compression. So you take this thing, you take blocks, you replace them with their averages or the maximum value in their blocks, and now you get a compression of the image down to this pooling layer, which then you can do another convolutional layer to another pooling layer and so forth. So a lot of these network architectures, if you look at them, you start off with a large convolutional window and you progressively refine it through many layers of this network all the way down to some very small pooling layer at the back end, which eventually you splay it out back into fully connected network out to the output. So let's call this a paradigm of computer vision structure. Lots of convolution, lots of pooling, high dimensions to low dimensions, pooling, convolution windows that are big and progressively refined to be small. And what's interesting is there's a lot of information about the filters that these things eventually essentially produce in producing features for the image classification. All this is learned through a training set. Now, as critical as the architecture and having high performance computing is, what really is important is have enough data to train all those network weights. You know, structures like this can have billions of network weights. So the only way you can really use the full power of a deep convolutional neural network, such as this one, is to have an equally sized training data set. And this is why ImageNet was so important in 2012. Up to that point, you had hundreds of thousands of labeled images with ImageNet, you had 15 million. It was that 15 million. It was that very large data set that allowed us to come to an architecture like this and exploit it to its maximum. So this is a paradigm. So I just want to highlight that this is a structure that is being used widely in the community. It's very expensive to train, but it's also extremely robust and successful, especially for images. So that's something I want to highlight here, that's kind of one of the interesting things. And a lot of people have vision applications where an architecture like this is really exactly the kind of paradigm of a network you want to use. And in fact, a lot of modern high-performance neural networks are basically playing around with different mutations of this kind of basic core structure. So you can certainly take a look at any one of the leading dominant conferences on, the conference on computer vision, CVPR, and you'll see year by year, or NeurIPS, you'll see year by year, especially in the vision field, improvements, but basically on thinking about ways to permute this kind of basic architecture to keep improving performance, to beat even human performance on vision tasks. So with that in mind, I just want to show you that network architecture and deep convolutional neural nets are extremely powerful, at least for this kind of problem where you're looking for structure that has features that are across scales. And the convolution is really helpful to pulling those features out and helping you make a classification decision accordingly. What I want to do now is walk you through a code in MATLAB to just show you this in practice. So I have a code here, and it's not too hard to run or operate, and I'm just going to walk it through and show you how easy it is, in some sense, to train one of these neural networks. I mean, essentially, whether you're using MATLAB or using TensorFlow with a Keras front end or PyTorch, all these things make it extremely easy for you to implement a deep convolutional neural network architecture. So let's walk through some of this code. So the first thing here is to download the data. So this is a data set provided within the MATLAB framework, and so this is just basically pulling that data set in so that we can actually do the training required here. So what this data set is actually, these are something like the MNIST data set, but they're digits, handwritten digits. And here's an example. I randomly pulled out 20 of these. This is what this first set of code does here, is what it's going to do is going to pull in this data. We're going to go randomly, there's 10,000 images. We're going to go randomly pull out the first 20 of them out of this and show them here. Okay, so this is what this is doing, is just go grab this data set. Let me show you an exemplar of this. And in fact, I'm going to take 20 random images, and this is what they look like. So you can see these are digits, handwritten or otherwise. They have rotations. Some of them are of high quality, some of them are low quality. But the point is, with 20,000 digits, the question is, can you write a code that can successfully take any of these images and correctly label it? Okay? So one of the early successes of machine learning was in the application of such computer vision techniques to the MNIST dataset. MNIST dataset was handwritten digits, like these. And this is work done by Jan LeCun and others while he was at Bell Labs, because what they wanted to do at the post office is put a little computer vision reader, read off zip codes, and send mail to the right place just by having a computer read off the zip code versus having a human have to make that decision. So you wouldn't have to accurately recognize handwritten digits. And in fact, that was one of the earliest uses of computer vision, was in that task. And so you start seeing, this is the difficulty of the task, is to label some of the more problematic data, like this one here. I think that's a 5. You know, that 7 is a little bit faded and off to the side. So some of them are very easy, right? I mean, this is a 0. but some of them are harder and have some ambiguity, even to the human eye. So how would a computer do, and how would we set up a neural network architecture to have a set of layers to take an image such as this and to start learning how to map it from an input space, which is pixel space like this, to a label, which is 0 through 9. That's it. Okay, so let's talk about how this algorithm works. So the first parts of this is just showing you the image. And so now we're going to start training this thing. All right, so we have labels in this data. And this is coming from us from MATLAB. It's a pre-built data set for people to use. And of course, there's a lot of data sets that are out there that are very easy for people to use because this provides a perfect training ground for trying new architectures and seeing what happens when you perturb your architecture, what's the performance like when you change things around. So here's what we're going to do. First, I'm going to specify how many training, how many number of files I want for training. So 750, and I believe this is for each different digit. I have 10,000 images, so I'm going to take 750 from each class and start training with those. So the nice thing is then, that provides me a lot of data, right? I have 750 examples with the correct label. And so what I'm going to start doing is across all of all of those digits, I'm going to have 750 examples with correct labels to try to learn a neural network architecture, a deep convolutional neural network that correctly maps an image to its label. That's the goal. And so this is what you specify here. Okay? This, here we're going to do this. We're going to take this data and we're going to split each into a training example. In the training, we're going to randomize that training example. Okay, so the training is going to come from number of files. It's going to be randomized pick from those. And this here has to do with essentially how do you seed this thing so that, like for instance, what you want to do is seed a random number generator. So if I run it here and you run it on your laptop, we both start with the same random initialization. Okay, so that's what that is actually doing here. So let's build a neural network. So here it is. Even easier than baking a cake. Kind of really is, because all you have to do here, look at this, you just specify the layers. I'm going to have an image input layer. These are 28 by 28 by 1. So I specify, these are black and white images, 28 pixels by 28 pixels. So I specify what's coming in. Specify the size of the input layer. Now it's interesting, right? I can run this very easily on my laptop, but imagine putting in 4K video or HD quality stuff here. So your input layer is much bigger, and it's usually by 3 because it's color. So you have the RGB cube. So your input data can be massive, okay? But it's already going to tell you that's the input. That's what you're going to come in with. And then you can just see what we build from here. Once you come in on the input layer, first thing I'm going to do is go to a convolutional 2D layer. And what I can specify here are 2 parameters. And these are the 2 parameters that are going to tell me a little bit about what normally you're going to specify is you're going to specify what my stride is and the size of the convolutional window. Okay? So those are the parameterizations that you would have and also how many layers do I want to make, right? So if you remember, I went from 1 layer to many layers, and the way you get those is through different random reseeds so that I can build different transfer functions. And I believe here I've put 20 transfer functions, convolutional window size 5. Okay? So you're going to slide across with the window size 5, and I'm going to make 20 layers coming out of this thing. And what I'm going to do now is specify, when I go through this layer, that it's a ReLU layer. That's what this is here. So there's the ReLU layer. Okay? Now, so that builds my first layer. I'm going from my input through this convolution with a ReLU. From there, I want to go to this, a max pooling 2D layer. And notice here, I'm going to pool over size 2 windows, grid sizes of 2, with a stride of 2. So I'm going to basically walk this through. I'm specifying how big I want the pooling level to be. So if this thing has a certain size, it's taking 2 pixels at a time. It's a 2 by 2 pixel map, sliding it 2 every single time, all the way across. Okay? So that's the max pooling. And so all I'm going to do here is go through 1 convolution, 1 pooling, and then I'm going to come back out. I'm going to do a fully connected layer, size 10. Softmax is a way of doing the classification on the back end, and then finally a classification layer. Okay? And then what I would suggest is there's lots of different neural network type architectures that can come into this. So there's convolutional layers, pooling layers. There's ways to do classification like softmax or classification layers. All of these, if you just do help in MATLAB or MathWorks, you can find a lot more information about what they actually do. I don't want to go into details to these specifically because these are just generically picked out of here, and I can use other types of processing through this, but this is just a representation of what some possibilities are. So that's it. So what layers does is tells you, here's the structure of a neural network. Layers just basically the graphic I gave you, which is here. Let me show it to you. So when you look at something like this, before I train anything, I can specify an architecture. I can tell you about the input, convolution, what are the functions I want, and going from here to here, how do I want to go from the convolution to the pooling layer, what size of things, do I want more pooling layers, fully connected, thresholding. So this architecture that I drew here, okay, that is fully specified in the layers command. So you get whatever you draw here, you can specify through that layers function in MATLAB. Okay? So we only did 1 convolution to pooling, we took out another convolution and pooling layer, but you could easily put them back in if you wanted to. In fact, you can see here kind of how easy it is. You want to add another convolutional layer after the max pooling? If you want to do it, just copy and paste, put them in there, and determine the sizes you want. It's kind of that simple. So this architecture, look how simple it is to write in some way. And by the way, this is the case for both MATLAB, Keras, Scikit. All of these are very simple command architectures to do very powerful things for you. Now, we haven't trained anything yet. All we've done is said, here's the architecture. This is the blueprint for the neural network I want to construct. What's going to come next is some options. Let's talk about these options. Training options, SGDM, Stochastic Gradient Descent Method. That's what SGDM stands for. So I'm going to go tell this thing to go train it, use stochastic gradient descent. There are other optimizers there as well. Maximum number of epochs, in other words, how many times do I want to keep going through and updating the weights towards getting the final solution. And the initial learn rate. So the maximum epochs and initial learn rate are all associated with that gradient descent, right? Remember, the learning rate is how big a step do you want to take each time you learn something new and compute a gradient towards getting you an update on the weights. So this is what this will do for you. Okay? So you can set lots of functionalities there. And then let's go train it. One line, train network, and I call the output convnet, so that's for convolutional net, so this is my own output layer. So what it's going to give for us? I'm going to give it the training data, I'm going to give it the layers and the options. Okay, so remember the train digit data has the images and their labels. The layers tells you the architecture, and the options tells you how you want to optimize. This runs the stochastic gradient descent for over 20 epochs, and then it gives you a result, which is convnet. So now what I have is convnet is actually now my model, right? This is now I can take this model, run new images through it, and it will produce out a label on the back end. So how do I want to do it? Well, here, I can take this now and test it. So I'm going to use the classify command. It's going to basically classify. It's going to say, take that convnet model that I have And now, instead of the trained digit data, so trained digit data is the training data for the digital data. And now I have this withhold set called test digit data. So this is the test set held out. The test set I held out, I want to run it through this classify command using this ConvNet model that I just built. And I get some results. And then I can test my results versus what the actual labels were supposed to be. And so this is going to give me my accuracy. So I trained on a set of data. Once I get that model, I can pull it out, run it on new data. And on that new data, I get some scores. And so I'm going to get those scores through the accuracy command. But you can see here, very compact architecture. But by the way, this can take a very long time to run. In this example, it's not too big because my images are just 28 by 28. They're small compared to what they could be. But if I had lots of data and I had, 3,000 pixels by 2,000 pixels, then this would be very expensive, and I'd have to let it run for quite a long time before I actually built this neural network model. But this is not so bad. And in fact, the result of this, let me just show you. I've already pre-run this. Oh, I had pre-run it. And then your accuracy scores, actually, let me just run this section here. When you run this section, here's what it does. This is now starting the training process. So here it is. I'm now running this code, and it's telling me the epochs and the iterations per epoch and the time elapsed. It's giving me some important information here. Let me actually widen the screen out so maybe we can see more of what's there. There you go. And it's starting to show you the accuracy and the time elapsed. Now notice what's happening as I progressively train this. Look at the accuracy. My initial accuracy, and this is a mini batch. In other words, it's testing it on a small subset of the data first to just see how it's doing. You can see this thing started off at 8%, which is even less than a 10-sided coin flip because there's 10 digits. And within one epoch, it's at 55%, and now after 11 epochs, look at that, now 12 epochs, you're at 98% and a little bit higher, right? And remember, it's stochastic gradient descent, and it's a mini batch accuracy. So it's not, this is why sometimes the accuracy will appear to go high and then come back down a little bit, is because you're looking at sort of these mini batches. But now you're in the very high percentages. In fact, after 16, 17, now in the near 100%. Again, a mini batch, so what I have to do is test it over a broader range because it's still actually iterating to bring the error down. So this is the kind of thing that you can do within this, and remember, this is a very simple toy data set, so it actually trains pretty quickly, and your overall accuracy after training is 95%. Okay, so remember the mini batch was not a good indicator of how well you're really doing, but the 95% is. So the 95% accuracy on a very simple test set like this gives you some idea of how well this thing can actually train a neural net for classification of the images that I've shown you here, which are things of this style here. Okay, so this is a nice little example, only in the sense that, obviously you're going to probably consider harder problems, but this kind of structure, look how easy it is to build. Right? It's very modular, very simple. You can have a lot of flexibility of how you play with it, how you put layers together, how many layers you want to put together, the size of the layers, the strides, the convolutions, the poolings, and you can give it options about how you actually want to do these optimizations, and then one line of code, go train the network. You just tell me the structure, tell me the options, train, and I'm going to give you back a model, and then you can see how well it does. So this is sort of the modern way of thinking about neural networks, because what it's really telling you is within architectures like this, you can very easily specify them, determine how you want them optimized, run, and of course it can take a very long time to run that optimization procedure, but it gives you back some very interesting results. And there's no arguing with the incredible success that these neural networks have had on image and vision processing, and why they in fact are now sort of the canonical go-to method for computer vision applications such as self-driving cars and autonomous vehicles. And so you have now that disposal of that at your fingertips. I'll again highlight all this lecture, all the code can be found here at databookuw.com. This is from the chapter 6 of the book by Brunton and Kutz. And if you want to download the PDF of the book, here it is, databook.pdf off of that website. And you can see all the details there, not only MATLAB code, but equivalent Python code to go with this as well. And so it gives you lots of flexibilities to start training more complex neural nets within this kind of architecture.